This is a video to cover one of the 4 intro skills, unit analysis. The idea behind unit analysis is that we take equations throughout the year of which we know these units already. Quickly, let me just kind of go over, obviously, meters, seconds. When you get to these fractions, they do this kind of in this, because I'm limited by Microsoft Word in this sideways fashion. I highly suggest you do a more vertical setup on your fractions. So meters per second squared, obviously kilograms, you probably know. This is 1/seconds, and this right here should be kilograms times meters per second, or if you would like, kilograms times meters per second. Now, the idea behind this is we want to look for one of two things. Number one, find unknown units. So let's go find unknown units is the first process that we're trying to do with unit analysis. The second one is check equations validity. I think that's a good way to put it. Okay, so these are the two purposes that we'll go over. Let's start with the top one. Okay, say that we have an equation such as this, where I have an unknown variable that I'm not sure of. So I have b equals a over t. Okay, what you're going to do is you can kind of put it underneath or over to the side, but you're going to replace the variables over here on the right side with their respective units. So a is meters per second squared. By the way, if you haven't yet already, as you can tell, it's probably not the worst idea to come over here and copy down those units. So maybe hit pause real quick, copy them down real quick, because you're going to see I'm going to move. So you're not going to be able to see this the whole time. So once again, so A's units are meters per second squared, and T's units are in seconds. Are the brackets necessary? For me, yes, for the first step. The brackets kind of tell the reader that you are talking about units and not talking about numbers. And it's also just a quick way for me to check as I am reading your work that you just simply have the right initial units. If you don't, obviously it's going to be off. Now, the next work that you show, I don't care if you do. So now if I transferred it, say, over here, it would be meters per second squared per second. Now, the only thing you have left to do is simply simplify the units. Now, be careful, particularly when it comes to this type of complex fraction, because you might look at this and immediately go, oh, the seconds cancel. Well, technically this is a complex fraction because this is, on top we have meters per second squared, and on bottom we have, as I just made it, seconds over 1. So to simplify a complex fraction, we multiply by the reciprocal of the bottom. Now, when you do that, you'll notice they do not cancel. In fact, it should end up as meters times seconds to the third. And that serves our first purpose, find the unknown units. What does that mean? Well, if this is the units of the right side, then B has those exact same units. Let's try again with a unit that or equation you'll see later this year. K equals 1/2 mv squared. This equation highlights a couple of problems that students struggle with. For starters, 1/2 is a scalar multiplier, or technically a divider, but it adjusts the overall number. What it doesn't adjust is the units, because it doesn't have any units. Like, for example, if I said this length is twice the width, and you knew the width was in feet, you also know the length is in feet because 2 doesn't have any units whatsoever. So when you do this, if you have a 1/2 or a 2 or a 3,840, and that's by itself and it's a scalar, then there are no units. You really don't have to put anything, or if you'd like to put something, you just put a 1 because it doesn't have anything. Now, the others of this part, okay, so multiplied by kilograms, that should be easy. That's just mass. Now, on the other hand, to the scalar, if you have a exponent, that does affect things. In the same way as if I said area is equal to length squared, this should have the units of feet, and this should have the units of feet squared, or, sorry, SI units, meters and meters squared. So what does that do to your overall problem up here? Well, you'd once again, in brackets, put the units for velocity, which should be meters per second, and then we would square everything inside. So the final units for this are kilograms times meters squared over seconds squared. Those are in fact the units for K, which again, we'll talk a little bit about later on. So once again, the first thing that unit analysis does is it finds the unknown units of a variable we haven't tackled yet. Okay, and put those brackets on the very first one, and then beyond that, you're simply going to simplify. Now, let's come over here to the second step. Change the equation, check, I'm not reading my own handwriting. Check the equation's validity. In this case, move this down, okay? We would look at an equation that we do know all of the units for. For example, we've probably seen this one before, or you're going to see it very soon. Delta x equals v times delta t. We know that delta x has the units of meters. We know that v has the units of meters per second. And we know that seconds has the units of, my apologies, velocity has the units of meters per second, and time has the units of seconds. And that's seconds over 1, technically. If I cancel the seconds on bottom and the 1 on top, you'll see I'm left with meters equals meters. This is correct. It should have the same units on both the left side of the equation as the right side of the equation. So if this was your problem, you'd be done with your work, and you would say, what is it? Oh, sorry. My apologies. I almost screwed up what I was about to write down. Okay, dimensionally correct. Now, what does that mean to you? It means this equation is possible. It might not be perfect, but it is in fact possible. On the other hand, let's look at another problem here real quick. Let's say I said something to the effect of x equals at squared over v. Okay? And I wanted to see, is this equation correct? Well, once again, we do the same things. We're going to take x, see that its units are in meters. A's units are meters over seconds squared. Times units are in seconds, but that is squared. And that's all divided by meters per second. Put the brackets on that yet. And now we simplify, okay? So I usually move downward with this, and again, I'm going to drop the brackets after the first one, but meters equals, let's see, that's going to cancel with that. So now I'm at meters over meters per second. Once again, highly suggest that you do the work here. Multiply by the reciprocal of the bottom. Cancel. And this meter is technically on top, so it cancels with that. And we have our final answer of meters equals seconds. So this would be dimensionally incorrect, and you'd write that over there, but my handwriting's terrible, so I'm going to leave it alone right now. One last thing to show you, and then we're all done. Practice, is an equation that you will see throughout the year. That is delta x equals vi times delta t plus 1/2 a delta t squared, and this kind of brings everything home. First thing to mention, deltas, the change in something, that has the exact same units as the thing itself. So if you see delta x, its units are still going to be meters. Same thing is true of subscripts. Subscripts, just kind of a descriptor. They don't change the units. So this should have the units of velocity, meters per second. And once again, we have time. Plus, as we mentioned before, that has no units, so technically a 1 or nothing. That's meters per second squared. And time is going to be in seconds. So here's how I would show this work. 1, my seconds cancel right here. 2, my seconds squared cancel over here. And I'm at this spot right here. Which brings me to my final point. You could really stop here, and this is in fact dimensionally correct. If you did simplify, meters plus meters does not become 2 meters like you'd expect. And the reason why is we don't know what the numbers are here, meaning I could plug a bunch of numbers up to that term and might end up with 20 meters, and I might plug the numbers into this term and end up with 40 meters. So this could be 20 plus 40 or 10 plus 5, who knows? But meters, any amount of meters plus any amount of meters are still going to end with the units of meters, meaning, imagine I told you that a distance was 10 meters, and you were to add 2 meters more. You were to walk 2 meters more, and I said, how far did you go? Really easy stuff, 12 meters. Notice 1 meter plus 1 meter is just meters at the end, so that's all we're trying to say here. Now, on the other hand, let's say I had started slightly different at the very beginning, so this would be a different problem, but let's assume this squared was not up here. Okay, it was just to the first, which would mean this would not fully cancel. This would be just seconds, which means this would end up down here. So one of those would cancel, and right now we would be at meters equals meters plus meters per second. At this point in time, there would be absolutely no reason to continue simplifying. I suppose you could, but it's just going to make your life difficult. And the reason why is when you add two things, they better have the same units. If they don't, that just doesn't work. Meaning, if I were to try to add a length and an area, meters and meters squared, that doesn't make any sense whatsoever. So point is, you don't need to try to simplify past this spot right here. You can immediately come over and just say, based on that, since those don't add together, it is not dimensionally correct. Terrible handwriting, all right, and back to the beginning. Just a simple reminder of what we're doing here. 1, dimensional analysis. Your goal is either 1, find unknown units, or 2, check the equation's validity. If it's dimensionally correct, it doesn't 100% mean it's the right equation, but if it isn't dimensionally correct, there is no way that equation can possibly exist. And that's dimensional analysis.